Now is talking about naming formula writing, although we do have one more quiz popping up on Friday. What we're going to be doing today, tomorrow, and the next day is looking at chemical reactions and properties of organic molecules. All right, and why don't I flip this to a screen that's bigger? There we go. All right, so what we got right here are alkanes, including cycloalkanes. Just some basically facts, descriptors about them. They are nonpolar, which means their electrons are
nonpolar.
That's right. Equally shared. Equally shared. So there's no dipole moment. Is there something? Do we talk about intermolecular forces? Does that ring a bell?
Yeah.
Yes, it does. So what type of intermolecular force is present? Just dispersion. Just dispersion forces, also known as van der Waals forces or London dispersion forces. And that's caused by the random movement of electrons, and they're going to form a partial positive, partial negative for a split second, and then dissipate and move around. All right, so that's alkanes, so very nonpolar. So thinking like vegetable oil or gasoline, nonpolar. It doesn't mix with water, right? Because water is polar. Have densities between 0.65 to 0.7. Is that denser or less dense than water? Less, because water is 1 gram per milliliter. So it's typically less dense than water. That's why it floats on it. Oil floats on water. Have low melting points and boiling points compared to other families of organic molecules because they have bless you, yeah. They have few intermolecular forces, just dispersion, which is weak. All right, boiling points. Increase in larger alkanes due to increased dispersion forces. So that means you go from methane to ethane to propane to butane. Those are all typically gases. And then we get to, what is it? Pentane. And you know from experience making esters that pentane is actually no, we didn't do that with esters, but pentane's a liquid. So, and then we get to octane and nonane and all those, and they get bigger. All right, are lower for branched alkanes because they have fewer contact points. All right, so let's draw a picture to show this. So here we got 1, 2, 3, 4 carbons. 1, 2, 3, 4. These are what you call it. Isotopes?
Yeah, isomers.
No, isomers. Isotope. Anybody know what an isotope is?
A different number of electrons.
You got it. Isotope has the same number of protons and electrons, but different number of neutrons. Isomer, they have different structure, but same molecular formula. So lower for branched alkanes. Talking about boiling point, because they have fewer contact points. All right, so drawing, what does it mean to have fewer contact points? All right, well, let's do this versus this. All right, which one has fewer contact points? The branched alkanes, because they're more spread out, where here they can just, rest on each other. They can stack like chairs. So you got all this dispersion interaction, dispersion. Here you got, a little bit of dispersion, but not as much. Therefore, the more branches there are, the more alkyl groups, the more the boiling point will be lower. All these concepts, oh my gosh. All right. It is. They're higher for cycloalkanes because their rigid structures allow more contact and attraction between the molecules. So let's just draw, a cyclohexane. I should have drawn butane because it's easier to draw. But. All right, hey, look at that. So you do have more opportunity of contact points where here you don't have as much. So you're going to have a slightly higher boiling point for the cycloalkanes, but the max amount for the alkane. All right, alkane uses. We got methane, ethane, propane, and butane are gases at room temperature and used as fuels. Usually propane is the fuel of choice for Memorial Day and outside grill outs. Methane, that's what comes out of the gases that we use for Bunsen burners. And then ethane, methane is also produced by cows and all that stuff. And people. All right. Alkanes with 5 to 17 carbon atoms are liquids and found in gasoline, diesel, and jet fuels. So once you go beyond the gases and start becoming large enough to be a liquid, then it's used in fuels. All right, and we got a little picture right here showing different uses of crude oil, and you can probably see it better on your actual sheet in front of you. But what they do is when they refine it, one of the reasons gasoline always jumps up in price or is higher is because there's not many refineries in the U.S. which allow us to take crude oil and make it into gasoline. So when there's a refinery that's down, then the gas price will shoot up. All right, so it looks like diesel. So once they boil it off enough, it'll have diesel, and then we got kerosene, petrol. As we go further down, we got bitumen, which is good for like pavements and roads and stuff. All that thick tar stuff you can't really put in your car. So these are all basically alkanes, oil. 18 or more carbon atoms are solids and found in the waxy coatings of fruits and vegetables, like apples. Except a lot of the stuff that you get at Pig and Save, the wax is fake. They wax it, I think, just as a preservative to make it look nicer. All right, difference in boiling points are used to separate hydrocarbons and crude oil. So that's what a refinery does, boils it in a safe way. And heating to a higher temperature produces gases that are removed and cooled. All right. And that's just crude oil, the easy to oil. In North America, they got oil shale where they crush sedimentary rock and squeeze out the oil. All right. So those are some properties of alkanes. Now we're going to do some basic chemical reactions, and this is something that you've already kind of done in your chemistry career, combustion reactions. So alkanes are typically not very reactive due to strong sophomore year carbon-carbon single bonds. The most typical reaction is combustion. So what's one of the reactants of combustion?
H2O.
No, that's a product. Oxygen. So you got some sort of hydrocarbon and oxygen producing water and CO2. Okay, good thing we're reviewing this. All right. So you got alkane plus oxygen produces CO2 and water and energy. It's what makes the world go around currently, pretty much. All right, example. We got. Anybody know what molecule that is? Propane. Or some no, it's propane. Yep. Because I don't think there's any isomer of propane. So, and that's oxygen. Good. And this is supposed to be an arrow. I don't know why that's missing. 5 oxygen. Oh, bummer. This example is done for us already. All right. But so we got to balance it. So let's do this one. Complete and balance the reaction for the complete combustion. Oh, do you guys remember the difference between complete and incomplete combustion? So complete combustion produces CO2. Incomplete produces CO. What happens in your furnace, especially right now, both are being produced. Incomplete and complete. CO2 and CO. Why don't you die of carbon monoxide? Well, because it's properly vented. Hopefully. If it's not well ventilated, hopefully you got carbon monoxide detectors and you didn't go to Home Depot and get the dual ones, smoke and CO2, because those are unfortunately useless because CO2 is heavier gas and it's going to linger towards the bottom, so it's not going to go to the ceiling. So by the time it hits the ceiling, you're already done. So you always put a carbon monoxide detector at hip height. Never buy a dual. I don't even know why they make those. It's and then another thing, they only work 70% of the time. The ones from the big box stores. Yeah. So you got to go to like a commercial grade one.
That's scary.
It is, yeah. It makes you feel safe though.
You can't smell it. You
can't smell it.
Just go to sleep, right?
Yep. It basically, the carbon monoxide attaches to your hemoglobin, red blood cells, just like oxygen does. But unlike oxygen, it doesn't release.
like it traps in you.
So you get suffocated at the cellular level. That's carbon dioxide or carbon monoxide poisoning.
How do they fix something like that?
That's a good question. So,
Like if they catch somebody who like, had just passed out from it, because obviously they're not dead yet.
Yeah, maybe it releases after a while, just not soon enough for the red blood cell to do what it's supposed to do and transport the oxygen. So, because I'm sure over time it releases. Because when you get carbon monoxide poisoning, you need to rest a little bit and then recover, and you'll recover fine. So it's not permanent. But it's permanent enough that it disrupts the amount of oxygen you need to live. All right. So in this example, it says complete combustion. So that means one of our products is going to be CO2. Incomplete is carbon monoxide. All right. So it's always CO2 and water if it's complete combustion. And then from here, it's just a balancing problem. I got 7 carbons, so I need a 7. Nice. I've got 16 hydrogens, so I need a 8. That gives me 14 plus 8. Oh my god. 22. Guys, you are quick. Oh, 22 divided by 2 is what? 11. So we got, there it is. So that could pop up on an IB question in May. Oh, how about the complete combustion of ethane? Okay, ethane. What is ethane? We got CH3, CH3. So that's C2H6 plus oxygen. Reacts to form CO2 because it's complete. H2O. Nice. We got 2 carbons. What goes here? 2. We've got 6 hydrogens, so we need a 3. Oh, we got 4 plus 3 is 7. 3.5 times 2 is 7, but we can't have a decimal coefficient. Oh. So we got to multiply it all by 2. And that's the quick, easy little trick to do it. So it's a 2, 7, 4, 6. Oh, we haven't done balancing in a long time. This is fun. Yeah. Oh, how about incomplete combustion of C7H16? Hey, that's like the first one, kind of. So a reactant is going to be O2. A product is going to be CO. CO.
Carbon monoxide, right? Then I'll kill you.
Plus H2O. 7 carbons. Need a 7? Oh, probably 14. Yeah, 8 times 2 is 16. So 7 plus 8.
15.
Oh, yeah, 7.5. All right, so we're going to need a 2, 15, a 14. Oh, and a 16. All right. There we go. All right, speaking of CO2 and carbon monoxide, it produces pollution. Particulate matter is probably one of the biggest issues. As we can see at one of the global manufacturing hubs of the world, Beijing, China, you can barely see the traffic because there's so much smog. So that's a lot of particulate pollution. That's why they wear masks, because you're going to need to, otherwise you're going to die of respiratory disease. Said that CO2 is a greenhouse gas because it absorbs infrared energy. And then that's why we got the Paris Accord and all that stuff to help curb it. However, we got something called the tragedy of the commons, and that's if everyone is not on board, it's not going to work. So once one person doesn't do it, then we're all then nobody wants to do it. And one of the big things with the Paris Accord is developing countries like India and China are given a temporary free pass on reducing their emissions. They don't have to start reducing it until, I think, at least 2025. However, in a free market society, capitalism, it puts those that are in the Paris Accord at a disadvantage economically. And if they're just going to continue to pollute, all of that pollution travels throughout the world. So the tragedy of the commons, unless we're all on board. But then by eliminating it, that limits economic growth. So that's the big controversy with the 21st century and CO2. That's what the Paris is about. Yeah. So we got out of it, but then now we're just in it again. And we'll be back in the Middle East for more wars for their oil. We'll be back in the Middle East for more wars.
Oh my god.
Because it's cheaper to use that oil than our oil.
Well, now we don't have oil.
Not anymore, yeah. No.
Well, yeah, what does that mean for us? 'Cause I
Well,
never understood.
most of
Rely on the Middle East for oil.
so we became energy independent in the last 3 years because of oil shale, which we have huge abundance of in the Midwest, like Nebraska, and then in Canada. And it is a little more intensive. You got to put a little bit more energy, and it is a little bit more expensive to make because you got to squeeze and heat and crush out the oil from the shale. However, if we have too many regulations, that's going to shut those companies down, and then we're going to have to get oil from Saudi Arabia and Iraq, and then we're going to have to send troops over there and deal with all that and secure the oil, which is what we were doing the first 2 decades, pretty much, of the 21st century. And then the whole thing about electric cars, Tulsa. We could do electric cars, but you got to plug electric cars into your outlet. And where do you get your electricity from?
The city.
Yeah, which usually has coal-powered fire plants. Power plants. So, if we can't get off fossil fuels, why we could do solar, but that's the actual solution, yeah. So if we do solar, there's something that environmentalists don't like. I see myself, I try to be environmentally minded. And the concern with solar is it lasts for 25 to 30 years. What do you do with it after that? You put it in a landfill. But then now you got e-waste, which is more pollution to the environment around you, and that's not good over the long term either. So nuclear would probably be the best. Yeah, it produces nuclear waste, but it's a small amount, and you just hide it.
What happens when we have too much?
You dump it in the ocean with
Well, you put it in a deeper tunnel in the ground then. But it's pretty safe, just as long as you don't put it on a fault line, then you're good. So,
Or we can do it in Wisconsin.
Wisconsin would be a safe area. Find safe locations, and we do have some nuclear power plants.
Throw it on Chernobyl.
Yeah.
So the technology for nuclear power is much more sophisticated than back then. But ultimately, fusion would be the best, which is putting 2 hydrogens together to make helium and then excess energy. But we don't have that technology yet. So.
What's the deal with fission? Because I knew that for like nuclear weapons, I knew that the SAR bomb, that was a fission bomb. What's the difference?
Fission is splitting the atom, and then fusion is bringing 2 atoms together. So,
But they haven't sustained the way to do that.
well, you could probably make a bomb out of it because that's not sustainable. It doesn't blow up. Yeah. But to make it so it doesn't blow up, but still fuse it together, that's the hard part. All right. All right. So, Alexander, you all right? You all right?
We were talking about the sibling off.
Oh, okay. Well, here's something called global dimming. Global dimming. This exists, and they actually farmers throughout the world they do pan evaporation experiments because they want to know how much is evaporating and then how much water they're getting, and as a result, they can collect evaporation data. And what they're finding is over the past 30 years, evaporation rates have been going down a little bit. And the idea is there's particulate, basically smog, in the atmosphere that's preventing photons from the sun getting in. And because what is evaporation caused by? It's not caused by temperature. It's caused by the sun hitting it exciting the molecules so that they turn into a gas. That's evaporation. So if you have less sun rays coming in, then you have less evaporation. That's what's happening, and that's called global dimming caused by particulate pollution. So whether CO2 is causing global warming or not, we all do know that pollution is harmful to living things. And when we produce smog and all that stuff, probably not good. And here's one of the results, global dimming. So they actually think that maybe global warming is increasing faster than it is, but it's being offset by global dimming. So the pollution that causes global warming is also reducing global warming. So, because if there's less photons coming in, then there's less heat to be trapped.
That's so bizarre.
So. All right. But they're not, that's why they're not really calling it global warming anymore. It's more like global climate change, because there's more than just CO2 trapping heat. There's CO2 or particulates preventing photons from entering the Earth, basically. And then if you have different evaporation rates, now that's going to make something that was more fertile for growing corn less, and then your crop yields go down. So, which is not good. But we can get like cool iPhones for cheap. So, all right. So some more chemistry. Look at this. Alkanes. We got halogenation of alkanes via substitution reactions. So when alkanes react with halogens, a mixture of halogenated products is produced. In the reaction called substitution, one or more H atoms are replaced with a halogen, usually chlorine or bromine. So here we got an example. So the equation for the reaction of ethane and chlorine to give the monosubstituted product is, okay, yeah. So it's a three-step process. So ultimately what we're doing is we're producing CH3, CH2, and then Cl. So essentially that's kind of what's happening. And yeah, I put this in here in this spot since we're talking about environmentalism. This is a reaction that causes basically the ozone layer to deplete, essentially. And it's not with chlorine, but it's with fluorine, and it's called fluorochlorocarbons. So it's got a chlorine and a fluorine on it. And those are found in refrigerants, old school refrigerants. They're legal now. But back in the day we had them, and they would go up, the halogens, and they would mix with ozone, O3, which protects us from harmful radiation from space. And it would be basically a continuous reaction, a chain reaction. And just one molecule of hydrofluorocarbon would destroy many, many molecules of O3 until we had not a hole, but a thinning that was called a hole in the ozone layer above Australia, which is why there's higher incidence of skin cancer in Australia. But good news, I think it was in the late 80s, they had an international treaty agreement that they would ban globally fluorochlorohydrocarbons. And since then, the ozone has been healing itself over time. And in 2050, which now is only 30 years away, it'll be as good as new. So,
just randomly, I think one of the world's natural phenomena is in Australia. It's like a pink lake.
Oh, really?
Yeah.
Is it pink?
It's that chemical reaction that happens in the lake once a year.
Nice.
Turns like the whole lake pink. What?
Is it safe?
I don't know. I just
Probably not. I don't know. What?
New Zealand.
So that's an example where tragedy of the commons is reversed because everyone agreed to it. Then things happen in a positive way. So this Paris Accord could work if everyone was on board equally. But well, everyone wants their own thing. Yeah. China wants to be the global power, so can't be a global power unless you're pumping out fossil fuels.
Yeah, it's algae, I guess.
All right. what we got is a three-step process. So how does this ozone layer destroy? We're not going to use the example of ozone. I don't think this is just with methane because methane is the simplest. Let's stay simple. Initiation of free radicals created through homolytic fission. What is homolytic fission? Well, it's the breaking up of a molecule to form a free radical. So what are we dealing with? Cl. So we'll talk about free radical in 1 second. So there's chlorine. And what's going to happen is UV, stands for ultraviolet light, hits it, and that's what sparks the reaction to form chlorine into 2 chlorine free radicals. And so basically the Cl-Cl bond is broken by the UV and creates a free radical, which is an atom or molecule with an unpaired electron. There it is. It's just waiting to be paired up. So it's waiting to wreak havoc on anything it can wreak havoc on so that it can stabilize. So that's the initiation step. The next step